As humans, we can intuitively understand motion. We understand that if I hold my pen, it won't move. And if I release my grip on my pen, it falls towards the earth. But why does it do that? To understand why the pen falls towards the earth, we need to understand Newton's laws of motion. The first of which states that an object at rest will remain at rest, and an object with constant velocity will remain with constant velocity in a straight line unless otherwise acted on. Newton's second law of motion states that an unbalanced force results in an acceleration. Newton's second law of motion is helpful to us in this case. We can see that when I release the pen, there's an unbalanced force, which is resulting in the downward acceleration of the pen. Newton called this downward force gravity, and he explained it with his law of universal gravitation, which states that the force that an object feels is proportional to big G, the gravitational constant, multiplied by the mass of the first object, the pen, the mass of the second object, the earth, divided by the distance squared. What this means is that if the mass is increased of one object, so will the force. But as we know from F equals ma, if we increase the mass of an object, we increase the force that is needed to accelerate that object, meaning that all objects will accelerate towards the earth at the same rate. Although Newton's law of universal gravitation could accurately predict the orbit of the planets around the sun and the falling of an apple from a tree, he couldn't explain what the force was. 250 years after this, Albert Einstein discovered that the speed of light was a cosmic speed limit. This had some problems for Newton's gravitation. The main problem that arose out of Newton's gravity with this new universal speed limit is that Newton's gravity was said to be an instantaneous force, meaning if you took out the sun, the earth would feel the effect instantly. He then came up with a new equation for gravity and a new way of looking at it. This equation states that the presence of mass warps space-time. What does that mean? It means that any mass that is present will curve space-time in such a way to make straight lines, which light would normally be taking, take curved paths. This is how we see the phenomenon of gravitational lensing and how planets orbit the sun. These lines that the light is traveling are what we call geodesics, meaning that they are straight for all intents and purposes because no forces are acting on them. They are just following the curvature of space-time. How Einstein came to this conclusion that gravity is not a force, but a warpage of space-time was through his equivalence principle. He thought that if an observer in a box were stationary on the Earth's surface, it would be indistinguishable from an observer in a box being accelerated upwards at 9.8 meters per second squared, because they would feel a downward force of what we would call gravity. But this force was fake. So what's saying that the force of gravity that we feel on the Earth isn't also a fake force? Now, how does the warping of space-time create gravity? As we can see, we've got a two-dimensional surface of space-time here and a two-dimensional mass, being the sun, creating a gravitational well. What does this mean for gravity as in orbits? It means that the sun, having this three-dimensional gravitational well, will curve the space-time paths that would otherwise be straight, meaning that the Earth is taking a straight path through a curved space-time. What does this mean for the pen that we started with? It means that it should be following its geodesic line, and as soon as I release it, it will follow its geodesic line along the curvature of space-time until it reaches a force that will stop it in its motion, being the table. Therefore, because free-falling objects are following geodesic lines, this means that gravity is not a force, but a result of a four-dimensional curved spacetime.